Here we see that radio waves form a small part of a wide spectrum of waves, known as electromagnetic radiation, some of which are visible as light. The various types of wave differ in wavelength, frequency, and energy. Long waves, generated by an electric output through a radio antenna, have a low frequency, whereas ultraviolet radiation waves from the sun have a very high frequency. The frequency of the wave is proportional to the magnitude of the particle's energy. So, very short waves, such as X-ray waves, have a very high frequency and contain an enormous amount of energy. It is this energy that enables them to penetrate and even harm human tissue. Whereas the long wave, with a low frequency, requires comparatively little energy for its transmission and is harmless. Waves within the spectrum have similar characteristics, such as the speed at which they travel, namely 162,000 nautical miles or 300 million meters per second. This is known as the speed of light, but in fact, this is the speed of all forms of electromagnetic radiation. Electromagnetic radiation does not require a material medium and can travel through a vacuum. That is why this form of energy can travel to Earth from the Sun and from outer space. Where both a magnetic field H and an electric field E exist, the two fields are collectively known as electromagnetic radiation, and the frequency of these electromagnetic waves is the same as that of the electric charge which created them. The direction in which the electromagnetic waves travel out from the aerial depends upon the orientation of the aerial. If the aerial is vertical, then the electric field E also travels in a vertical waveform. This is called vertical polarisation. If the aerial is positioned horizontally, then the electrical field will be horizontally polarised. To receive maximum signal strength from an incoming radio wave, it is essential that the receiving aerial is in the same plane as the polarisation of the wave. So a vertically polarised radio wave would require a vertical aerial. The magnetic field H, which is also created by the alternating current, travels at right angles to the electrical wave. But we are not concerned with the magnetic field during further consideration of this topic, as it is only the electrical field that carries the radio message. Circular polarisation is produced by winding a wire in a helix shape around an insulator. This is called a helical antenna. The helical antenna has the advantage of transmitting in both vertical and horizontal planes, and in all planes in between. So, circular polarisation is useful where a transmission in a single plane, for example the horizontal plane only, may be rotated or twisted in space. This is called Faraday rotation. It occurs as the signal passes through magnetic fields in the ionosphere, which bend the wave and thereby reduce the effectiveness of the transmission. Consequently, circular polarisation is most often used in satellite communications such as GPS and mobile phones. Circular polarisation also has the advantage that antenna alignment is no longer critical, as the wave transmission is in all planes. When used with radar, circular polarisation has the benefit of being able to eliminate unwanted precipitation, clutter, from radar screens. However, the production of helical waves consumes more power than the production of vertical or horizontally polarised waves, and so range is less. Consequently, linear polarisation is used in good weather and circular polarisation is used in rainy weather.